Hi, everybody. This is Mrs. Hilt, and today's lecture is on acceleration. So, the objectives for today will be to understand how displacement and velocity are connected to acceleration and how to perform calculations with acceleration. And I apologize if you hear Gilly Cat meowing in the background. All right, so we have displacement and velocity, two things that we've already learned about, and we had a little review on that yesterday as well. Our new one is acceleration, but I am grouping all of these in the motion family. We're gonna think of displacement as like the grandpa. Velocity would then be the dad or dad, mom, whatever, and acceleration would then be the next child. So if you are the child, that means that you have a little something to do with velocity, where you came from, and you also have a little something to do with displacement, which that is all true for these words, even in physics. So displacement, we already know displacement is the change in position. And we can calculate that, displacement being our x, by subtracting the initial from the final positions. So let's do that in this example. While Jaron is traveling along a straight interstate highway, he notices that the mile marker reads 260. Jaron travels until he reaches the 150 mile marker and then retraces his path to the 175 mile marker. What is Jaron's displacement from the 260 mile marker? So there's some things in here that we don't have to worry about when we are doing calculations with displacement, and that would be that he has to retrace his steps. We only care that he ended at the 175 mile marker and started at the 260. So we need to find the difference between those. So Jaron's displacement would be 85 miles. All right, now the next step up is velocity. So velocity has displacement within its calculation. And what velocity is the rate of the change in position. You can see that the definitions for each of these, they really didn't change much. The only difference is that velocity has a rate. So the calculation for velocity will be very similar, just divided by time. Velocity is equal to displacement divided by time. Let's try this out. Okay, Hannah is at the mall looking for the new FIFA game. She walks 200 meters from her car to the first store, then realizes she forgot her purse. She returns to her car, grabs her purse, and returns to the same store. Hannah found the FIFA game and purchased it immediately. Feeling accomplished, she rewards herself by walking 150 meters to the food court and indulging in some delicious orange Julius. So I made this problem up and got a little carried away with myself. So let's draw a picture to hopefully not confuse you guys. All right, so let's make Hannah's car right over here. None of these will be drawn to scale. And let's make the shopping mall, all right, over here with her first store and then food court. All right, let's draw some vectors. So she first walks 200 meters to the store, forgets her purse, goes back and gets it, and goes back to that store. Remember, that is 200 meters. She buys a FIFA game and goes and rewards herself with Orange Julius, 150 meters away. So again, not drawn to scale, but I hope that my diagram made the problem a little less confusing. So what is Hannah's velocity? That is not even asked in. Oh, all right. This was not an updated PowerPoint. That makes it very confusing as well. So the question should have ended with it took Hannah so it was missing a part. Sorry about that. Hannah's trip took 8 minutes. What is the velocity in meters per second? Okay, so we will calculate this by figuring out what her total displacement is. So that is not the total distance that she's traveled, just the distance between her starting position and her ending position. So her displacement is 200 meters plus 150 meters. So 350 total. Then her time, we do need to have it in seconds. So let's first convert 8 minutes into seconds. Then we'll take that'll be 480. You divide that out and get 0.73 meters per second. So now I kind of ran out of room. I'll write it over here and circle it. There we go. Just gonna highlight that one, keep it consistent. All right, now let's try out acceleration. So first we'll define it like we did the last two again. So change in position, then the rate of the change in position. Now we will have the rate of change in velocity. So the equation again will look very similar to velocity, except the velocity will now be divided by time. Acceleration equal to, so changing velocity, final minus initial, divided by time. You could also see it as delta V or delta velocity over time as well. And the delta means the same thing in this class as it does in math class, change. Now let's apply that. If a train going 60 meters per second hits the brakes and it takes the train 1 minute and 25 seconds to stop, what is the train's acceleration? So we need to have the acceleration time be the same as up here. So we will first take our time and make it all into seconds. So we know that 1 minute is 60 seconds, so we can shortcut this by just taking 25 plus 60, 85 seconds. Now we'll take the velocity and set it up just as we did in the problem. Okay, and notice set it up just so we did in the equation. Notice that there is no initial or ending velocities identified, but it says that the train is coming to a stop. Therefore, the final velocity will be 0. So 0 minus 60 meters per second divided by the 85 seconds that it took to go from 60 to 0. So for this calculation, you will get a change of negative 0.7 0.7 meters per second. Meters per second per second. And that looks a little odd, but that's totally fine if your units do look like that. They can also be expressed as negative 0.7 meters per second squared. All right, let's learn a little bit more about velocity now. Okay, so here are some other facts about it. It is a vector quantity. Velocity is within it. Velocity has magnitude and direction, therefore acceleration does as well. Then you have the two different formulas, which you guys saw on the last slide. And again, the F means final and I means initial. Units displacement over time, or meters per second or meters per second squared. All right, and we are going to end it off with 2 practice problems, and then you guys will have some practice of your own. All right, calculate the acceleration of a cyclist if he speeds up from 3 meters per second to 5 meters per second in 10 seconds. So he starts at 3 meters per second, that is the initial velocity, and he ends at 5 meters per second, that is the final. Here is how long it took him to do so. 5 meters per second minus 3 meters, deleted for some reason, meters per second divided by 10 seconds. So you get 2 over 10, which is equal to 0.2 meters per second, or you can also say 0.2 meters per second squared. Put the 0 right there. All right, let's do one more practice problem. If you would like to try and pause the video and do this one yourself and then check your answers, go right ahead. No matter what, you guys are going to have some practice later on. Okay, if a swimmer swims at a constant acceleration of 0.05 meters per second squared and begins at 2 meters per second, how long has she been swimming when she reaches 3 meters per second? All right, so a little bit different of a problem. We have been given our acceleration squared. We have been giving an initial velocity, 2 meters per second. and the final velocity of 3 meters per second. So the only component that is missing from our formula is time. And this is a perfect example of when you guys will be using the equation to solve for other parts. You guys could also be solving for the initial velocity, final velocity at times. It's not always going to be just the acceleration. All right, and we'll set it up by just plugging everything into the formula. So 0.05 meters per second squared is equal to 3 meters per second minus 2 meters per second divided by time. I'm going to first simplify the top. Okay, and I like to solve these by cross multiplying, and since the other side does not have a denominator, it's an easy switch. So the time will end up being equal to 1 meter per second divided by 0.05 meters per second squared. Which that reduces to, or simplifies, to 20 seconds. All right, thank you for watching. Please let me know if you guys have, excuse me, any questions. Again, sorry about Gilly Cat meowing in the background. I hope that he wasn't too distracting. I also appreciate you guys putting up with my new videos. This is very new to me, and I apologize if there are a lot of hiccups along the way. All right, thank you. Bye.